Hi, my name is Justine Harkness, and in this video, we'll look at how to use the reaction quotient to determine how a reaction will proceed. We can use the values of Ke, Q, and Q to determine how a reaction will proceed. Now remember that KEQ is that ratio of products to reactants at equilibrium. You can think of this as kind of like the destination of the reaction. It's where everything wants to be. Q is the ratio of products to reactants at any point in the reaction. So this is like our current location. Now, just like you compare your current location to your destination on a map to determine which direction you need to drive, we can compare the values of KEQ and Q to determine how the reaction will proceed to reach that equilibrium destination. Now, in our first case, we can look at KEQ being greater than Q. Now, if we think about this as that ratio of products to reactants, if KEQ is greater than Q, that means that Q is too small. That means that we have too few products and too many reactants. So to get Q larger, to be equal to KEQ, we would want to increase the concentration of products and decrease the concentration of reactants. And the way to do that is to have the reaction proceed forward to create more products. Now, if Q is equal to KEQ, awesome, we are already there. We are at equilibrium, so we're not going to be shifting in any direction. This is where our forward rate of reaction is equal to our reverse rate of reaction, so we don't see any changes in the concentrations of products or reactants. Now, the last possibility is that we have overshot equilibrium, where Q is too large. Now, again, if we think products over reactants, if Q is too large, that means that we have too many products and too few reactants. So we want to decrease the value of Q. And we do that by decreasing the concentration of product and increasing the concentration of reactant. So if we have a Q value that is too large, the reaction will proceed in reverse to create more reactant. And we can think about this as kind of like the mile marker. So on this little diagram, we'd have the start of our journey where Q is equal to 0. We haven't gone anywhere yet. We'd have our destination. Maybe this is our perfect vacay spot or a lovely vacation. If we are currently far from our vacation, we're going to continue driving until we get there. That's where Q is still less than KEQ, but it's getting closer as we drive towards our vacation spot. Once we reach that vacation spot, awesome, we are there, we're going to stop driving. But say we missed a turn and ended up somewhere over here. We have definitely overshot where we wanted to be, so now we're going to start driving back towards our destination, going in the opposite direction. So let's take a look at some example problems and look at how to do this in chemistry. So here we are given an equilibrium constant of 4.84. We have some concentrations, a reaction, and we need to determine both the value of Q and then based on that Q value, how this reaction will proceed. Now the first step is to write out our Q expression, which would be the concentration of products over the concentration of reactants. So for products, we have NH3, have CO, and then as our reactant, we have HCO and H2. Now to get our value of Q, we'll just plug in our values for our concentrations. So we have 1.4 molar for NH3. We have 5.9 molar for CO. And then for our reactant, we have 2.5 molar. And if we crunch the numbers, this would give us a Q value of 3.3. So to determine how this reaction will proceed, we need to compare our Q value to our KEQ value. So here, 3.3, our Q is less than our KEQ of 4.84. So this means that our reaction will proceed forward to make more product. So now you should feel more comfortable comparing Q to KEQ to determine how a reaction will proceed.